Hello everybody, this is English for You, the program that helps you improve your English. A very warm welcome. A couple of days ago I received a letter from the cultural director of the Hungarian television, and he thanks us, the English for You staff, for the programs, and he regrets to inform us that unfortunately the Hungarian television is unable to finance this educational and cultural program. So this seems to be the last program, which is pretty sad. They are the cold facts. In the studio I have my Fazeka students not smiling this time, but I would like you to smile, because you either shed public tears or you smile. These two things show nicely on television, so I'd rather you smiled, okay? How's everybody doing? Dora?
Fine, thank you.
Great. Sobot?
Well, I should smile.
You're smiling, that's great. Victor, please.
I'm great, thanks.
Okay. How are you doing, Victoria?
Fine, thanks.
Splendid. Today's special guest is Professor Brian Cole from the United States.
Oh.
Brian teaches at Columbia University, and he's been in Hungary for a couple of weeks now as a Fulbright grantee, researching at KFKI, which is Központi Fizikai Kutató Intézet. Thank you very much for joining us.
Thank you.
And here, we have the first word card for you, and I would like you to help me with this word. What does this mean? Yankee. Victoria, got any idea?
It is a name for American people. It's degrading, I think. Not nice
Right.
to say.
So you shouldn't use, I mean, you wouldn't use this. You think it's a
No.
little bit insulting to call
Yes.
someone a Yankee? Right. To other people, I think Yankee means someone from the United States, but properly used, and I'm turning to you, Brian, what does this mean?
From my point of view, it means somebody from New England, which is the sixth most northeast states in the United States.
Is it insulting to call someone a Yankee?
No, in fact, we think of ourselves as Yankees and separate in that way from the rest of the people in the United States.
Right. So we can see the map of New England, which is, you can see the Atlantic Ocean here, and you were born in Maine, right?
Yes.
And this whole area is called New England. And I've read somewhere that there's a stereotypical picture of a New England Yankee. And it says that they are honest but shrewd. They are practical but thrifty. They don't like wasting money. And I've read that they are untalkative, and I hope it's not true, because this is a kind of talk show.
Well, actually, they're not very talkative to other people, but between themselves, they actually can be quite talkative.
And
So,
thrifty?
Very. In fact, your description would be a perfect description of my parents and grandparents in particular.
Right. Thank you. Now, it would be a shame not to sing a song which is called Yankee Doodle, and I hope that the lines for the chorus are going to come up pretty soon. So you can see the chorus here, and I would like you to join. Do you like singing?
Yeah, my voice isn't very good, but
Yankee Doodle went to town, riding on a pony. He stuck a feather in his cap and called it macaroni. Father and I went down to camp along with Captain Goodin. There we saw the men and boys as thick as hasty pudding.
Yankee Doodle, keep it up,
Yankee Doodle dandy. Mind the music and the steps, and with the girls be handy. Yankee Doodle, keep it up, Yankee Doodle dandy. Mind the music and the steps, and with the girls be handy. Right, thank you for the chorus. And we're gonna have a picture, and I would like you, Dora, would you say a couple of sentences about this picture? I hope it's going to be a typical New England scenery. Here we go.
There are quite many people on this picture. In the background, I can see a ship or a boat, and there's water. It might be the sea or the ocean, and yeah.
Right. So, thank you very much. I'm turning to you, Brian. This is a clam bake, isn't it?
it sure is, yes.
What is it?
What is a clam bake? It's a cookout on the beach.
Not a barbecue?
We wouldn't call it a barbecue. Basically, we frequently will cook lobsters, clams, mussels, and other
Seafood?
seafood by basically digging a hole, lighting a fire, covering it with seaweed, putting the food on top, and then covering it all over with sand and letting it steam for an hour or so.
Right, you mentioned this animal, which is a lobster.
Lobster.
Now, how big is a New England lobster? Would you like to show this? That
About-
big?
About that big. I mean, it can be, there are some that can be quite this big, but they're much more rare.
And which part do you eat?
All of it.
Oh, come on, this one?
The tail.
You must be joking.
No, well, I mean, you don't eat the shell, but the tail, the claws, and
The tail and the claws. And what color is the meat?
white.
And why is it red?
It's only red after it's cooked. It starts out a dark greenish black, and then when you cook it, the shell turns red.
It's hellishly expensive, isn't it? In Hungary, a lobster is hellishly expensive. Can you come up with a Hungarian name?
Homár.
Say it again.
Homár.
Homár, that's it.
Homár,
Right.
okay.
You've learned something, haven't you? Good. Now, thank you very much. Have you ever read a book, fiction or non-fiction, that had an enormous influence on you? If the answer is yes, would you put up your hand? Victoria, please.
So it was a couple of years ago, and it was my first book in connection with philosophy in a literature way, and it was by Jostein Gardner, he's called, and it was The Secret of the Card.
Why was it so important?
Because it raised a lot of philosophical issues that had not occurred to me before, and
Could you just mention one?
it was about how very much you must be happy that you live, because back now it's kind of complicated, but your grandparents and your great-grandparents and generations, there are more and more people, and if one of them died, then you wouldn't be born. You
Right.
couldn't live now.
Excellent, thank you very much. Victor.
Mine is a really famous book. It's Bram Stoker's Dracula. And I've read it, and it was, wow, it's
It
great.
changed your life.
No,
You decided to become a vampire.
yes, my thesis.
Right, thank you very much. I'm turning to you because you can see a very famous person here. Would you please say the name of this?
Yeah, this is Isaac Asimov.
And I think he had a very enormous impact on you.
Yes, when I was in the 7th or 8th grade, I read a number of science fiction books that he had written, and in the process of looking for his books in the library, I discovered some popular science books that he also wrote, where he translated modern science into things that average people could read. And in the process, I started learning very basic things about particle physics and nuclear physics, and I became interested, and I decided that that's what I really wanted to do.
Yes, so I think I've forgotten to mention that Professor Brian Cole is a physicist. Physician?
Physicist.
What's the difference?
Physician is a doctor.
So we have a physicist here. Be very careful. You can get confused easily with these two words. And he wrote his thesis, which is a long piece of work on a particular subject, usually for a PhD degree, right?
Yes.
And this is the title of Brian's thesis. Brian, would you be so kind as to read it out?
Sure. High transverse momentum particle production in heavy ion collisions at the alternating gradient synchrotron.
Right. Lazy afternoon reading. Sunday afternoon reading, right? Something
For a few people,
for a
yes.
few- I'd rather we didn't get into it right now at this stage, but we're going to come back to this. But let's start with some basics. And if you look at your desks, you're going to find a couple of word cards. And this is the time to show your word cards. And it's going to be pretty tough, you know, because I would like you to try and define these words in your own words. What have you got, Dory?
This is a neutron, and it's a particle which has no charge.
A particle which has no charge. I'm amazed. Yes, please.
This is the nucleus. Nucleus, or
Nucleus.
Lab.
Well, let's turn to Brian.
Nucleus.
Nucleus, yes, and the atom has two major parts, and one is the nucleus. It contains protons and neutrons, if I know well.
Very good.
Right, students?
Very good. Very bright.
This is proton, and it's in the nucleus, and it has positive charge.
Right, and yours?
Electron is a particle with negative charge.
With negative charge. Can you say negative charge in Hungarian?
Negatív töltés.
And positive charge?
Pozitív töltés.
Excellent! I can't believe it. See? Right. Brian, would you please come here?
Sure.
Because we can see the structure of the atom,
Yes.
and we have already mentioned a couple of, well, over to you. I don't want to.
Okay. All right. So we now have known for about a century that the atom consists. This drawing is not to scale, but it consists of what we think of as an electron cloud that occupies nearly all of the atom, and blown up so you can see it, but in a real atom, it's a very tiny part of its size at the very core is this thing we call the nucleus. And as you have pointed out, the nucleus consists of protons and neutrons, particles that are either positive charged or neutral. However, in the last 30 or 40 years, we've discovered that the protons and neutrons themselves contain other particles that we call quarks. And in fact, this is a illustration showing quarks that we call up and down quarks that make up the proton and the neutron. And this is important because the research that I do is focused on understanding the properties of how these quarks are bound up in the proton and the neutron.
Right. I just don't know how to read out these things. So, for example,
Okay.
the size of the nucleus. Would you be
Okay.
so kind as to read it out?
Yes, so let me give an example. The size of an atom is an angstrom, or 10 to the minus 10th meters.
Would you say it again?
10 to the minus 10th meters. So 10 to the negative 10th power.
Yes. Which is the smallest particle
Okay,
here?
so the smallest particle that has a well-defined size is the proton or the neutron, and those have a size of 10 to the minus 15th meters.
Right. Thank you very much.
Okay.
Would you sit down, please? And I want somebody to read it out. Nucleus size, Victor?
10 to the minus, I can see the
14th
14th meter.
meter. 10 to the minus 14th meter. Thank you very much. Now we're going to have a couple of very important words. The particle physics jargon or terminology. And again, over to you, because it would be very unfair to ask my students to try and define those,
Okay.
those terms. So,
Okay, so particle physics is a subfield of all of physics that studies the properties of particles and the way they interact and how they are made up. Properties of matter, for the work that I do, in particular studies how the constituents of nuclei behave under different conditions, particularly when you heat them up to very high temperature or compress them to very high density. Colliding, actually ing, nuclei is what we do in the laboratory to create matter at very, very high temperatures.
yes, can you come up with another word instead of colliding?
Smashing.
Smashing, colliding, right?
Right. And particle accelerator is a machine that we use to accelerate particles to very high velocity so that we can collide them and study what happens during the collision.
Well, I know my car, and in my car there's an accelerator.
Yes.
So if I push that pedal, the car goes faster.
Yes.
This is the accelerator. It's a little bit different.
It's quite different. The acceleration here is done through, you could think of extremely intense radio waves that push particles inside a tube in which we make the particles go in a circle.
Thank you very much. Now we are going to see something, and I would like you to say what's happening. Would you roll the tape, please? Would anybody please, Szabolcs, what do you think was happening?
something's happening. I could see. Maybe it was a collision in the beginning, and then it started. Something started to get created.
Yes.
So kind of collision. Anybody would like to contribute to this? Victor, please.
Collision.
Collision.
The atom bomb?
The atomic bomb, maybe. And what do you think collided? Dori?
Particles.
Say
Particles.
particles. Right. Very good guesses, very intelligent guesses. So we're going to review the whole thing again, but this time with your
Yes.
live commentary.
Okay.
All right. So
Okay.
would you roll the tape again, please? And Brian is going to comment.
Okay, so we start with two nuclei. They collide, and after they collide, the energy gets redistributed and starts producing many particles. In fact, in the collisions we study, 10,000 particles come out and expand very quickly. And in the end, the physics that I do is trying to study the properties of the particles created during this collision.
So in other words, two nuclei, because it's nucleus, nuclei. Very interesting plural, nucleus, nuclei. So two nuclei and so many particles
Yes, tens of thousands.
just from these two.
From one collision between two nuclei.
Fantastic.
Yes.
Thank you very much. Now, we are going to see a wider context of the research Brian is involved in. And again, the same task for you guys. You're going to watch this. What is happening? Would you roll the tape, please? When I was young, I used to go to pubs. And I used to play with pinball machines, you know.
Yes.
You have to push two buttons and there's a ball and it hits different things. But this was not a pinball machine, so let me help you a little. Victoria, what do you think was
Thanks
happening?
for your help. I don't have the faintest idea, but it could also be that these boxes have charges, so they quicken those particles, and that's how they keep them circulating and go their way.
So definitely particles. Would anybody like to add? Yes, Subwatch,
If the
please.
particle reaches a certain speed, it goes further, or goes through to the next round, or next way. Something like this happened.
Yes, thank you very much. Nothing. Okay, fine. I don't want you to talk right now because we're going to come back to this
Yes,
with
okay.
your live commentary. So
Yes.
at this point, we're going to see a fantastic picture. And over to you, Victor. What can you see in the picture? And it's going to be a huge something. Here we go. Victor, please.
Okay, I can see a map, kind of map from the view of birds, and there is a huge circle and a smaller one inside, and if I have to join this picture and the picture before, that maybe it's a huge tube or
You're very, very clever.
I don't know.
So what you said is from bird's eye view.
Bird's eye
Over
view.
to you. Would you come here, please, and
Sure.
show what we can see?
Okay, so this is actually a picture of the CERN accelerator laboratory, and as you in fact pointed out, there are several accelerators here. There are two, the smaller circular one and then a much larger one. This is many kilometers across from end to end, and these accelerators make particles move in a circle, and there are these what we call radio frequency cavities that make the particles go faster as they go around.
Excellent.
And okay.
Yeah, thank you very much. When I first heard of a particle accelerator, I thought it was a laboratory, and the particle accelerator was the size of a washing machine. But if you look at this, you can see how big it is. And we are inside, and this is in Brookhaven, right?
Right,
What
right.
can we see here?
Okay, so now this is at Brookhaven Laboratory where I do my research. This is one magnet This is a magnet made of superconducting. It's a superconducting magnet. It's 20 or 30 meters long, okay, and there are 1,700 of these magnets in the accelerator that I work at, and they're put end to end to make particles move in a circle.
Yes, we are going to have another picture, again from the inside of the Brookhaven laboratory.
So, right, this is what we call RIC, the Relativistic Heavy Ion Collider, and this is a sequence of magnets that make up one of the rings at RIC. There's another set of magnets behind that you can't see that make up the other ring, and those two rings make particles move in opposite directions so we can make them collide in our experiment.
Thank you very much. Now we're going to have a still picture of this animation, and we're going to take part in a virtual tour. And before that tour, I don't think we should fasten our seat belts, but we do need some information. Like what? So
okay. All right. So at Brookhaven National Lab, where I work, we also have to use multiple accelerators to get the nuclei moving at the very high velocities that we want. So there's actually 4 accelerators. There's what's called the tandem Van de Graaff accelerator. Particles come out of that. They travel through a very long tube, a beamline. This is a distance of probably half a kilometer, to another accelerator that makes them move faster. We then inject those particles into an even larger accelerator. When they come out of this accelerator, they travel down yet another, what we call a beamline, and the particles come out in bunches of about 1 billion particles per bunch.
That's what we're going to see, right?
Yes.
So if we start watching it, you can
Yes.
have a live commentary.
Yes.
Yeah. So would you please roll the tape, please, and over to you, Brian,
Okay.
with your live commentary. Right. It's going to be the pinball machine again.
So the ball that you see represents not a single particle, but a bunch, more than 1 billion nuclei traveling through the different accelerators. And as it goes through each one, it will start moving faster. When it comes out of this larger accelerator that we call the alternating gradient synchrotron, we take bunches and we make them go into the 2 different rings, rotating in opposite directions, and the bunches collide at 4 different experiments. These experiments then measure the particles that come out of the collision to study the properties of the matter that we create.
Right. And we have the first stop.
Right. So this is one of the experiments. It's called the STAR experiment. The next one in the sequence, sorry, not the next one. This is another experiment at RIC. This is an experiment called Phobos. And then the last experiment shown is the experiment that I work at. Here it is. It's called the Phoenix experiment. This is an experiment that this height is many times the height of a man, has something like 4,000 tons of equipment in it, and is quite large, as you can imagine.
Thank you very much. Now, thanks a lot. Now, I have this last word card for you, the Big Bang. Have you ever heard of the Big Bang? Dori?
I think this is the big explosion when the Earth, first became, or something like this.
Right. How can you link the Big Bang to the research you've been doing?
Well, okay, we've known for quite some time that the universe has been expanding outward from its very beginning. And if you imagine following that expansion backwards in time, very shortly after the instant that the universe was created, we think, the temperature was extremely hot, 10 to the 11th, many millions and millions of degrees. And matter at that time did not consist of protons and neutrons and nuclei. It was so hot that the protons and neutrons themselves didn't exist, and instead were broken down into the quarks, these things that are bound up inside them. And what we're trying to do in our collisions is create matter at that temperature again, basically produce matter in the state that it was a millionth of a second after the Big Bang.
So recreating?
Yes, over and over again. So
Right.
we want to be able to create that matter in these collisions so we can study its properties, and we get to do it over and over again, where the Big Bang only happened once.
Right. And why in Hungary? I mean, you came to Hungary, which is very nice, but is Hungary that advanced?
Well, there are people at KFKI who do research both in theoretical physics and experimental physics, actually at Brookhaven and on the physics of very high density, very high temperature matter, and I have collaborated with them in the past, so I had an opportunity to take my sabbatical here.
Right. Thank you very much. We've just had a New England Yankee in the studio. Thank you very much for joining us.
Thank you very much.
And goodbye, everybody. See you sometime. Bye.